Hey everyone, and welcome. Today, we are diving deep into something truly fascinating: neuropharmacology. I know, it sounds complicated, but think of it like this. It's the science of hacking the brain. We're going to break down exactly how certain chemicals can get in there and fundamentally change the way we think and feel.
And really, it all comes down to this one big question, right? How can a tiny little pill completely change how we think, how we feel, even how we act? I mean, it seems almost impossible that something so small could have such a massive impact on the most complex thing we know of, our own brain. Well, that's exactly what we're going to unpack.
Okay, so here's the game plan. First, we'll look at the brain's basic chemical code. Then, we'll zoom in on how a single neuron fires. After that, we'll see how they talk to each other and, this is the cool part, how drugs can jump into that conversation. And finally, we'll tackle the brain's built-in security system.
All right, first things first. If you want to hack the brain, you've got to understand its operating system. And what's amazing is that at its very core, our brain runs on this really elegant two-part system. A little bit of electricity and a whole lot of chemistry.
So you can basically think of it like this. The electrical part is the signal zipping down a wire, But at the end of that wire, it can't just jump across a gap, so it hands off a chemical message. And understanding this 1-2 punch of electrochemical signaling, well, that's the key to everything we're talking about today.
Okay, so let's zoom in on part one, that electrical spark. In the world of neuroscience, this has a name, the action potential. And really, it's the fundamental zap of electricity, the spark of thought itself that lets a neuron fire off a signal.
So this whole thing, this action potential, it's basically a super fast, perfectly controlled wave of electricity. It all kicks off when the neuron gets a signal. That signal makes tiny gates fly open, and bam, a flood of positive sodium ions rush in, causing this massive voltage spike. But just as quickly, those gates slam shut and a different set of gates open, letting positive potassium ions rush out, which brings the voltage right back down. Then, this little molecular pump gets to work, resetting everything back to normal. And the craziest part? This whole up and down dance happens in just a few milliseconds. That's the spark.
Okay, so that electrical spark we just talked about, it races all the way down to the very tip of the neuron. But now what? It's hit a dead end. There's this tiny gap, and the electricity can't just, jump across. So it has to do something clever. It converts that electrical signal into a chemical one. We call this the synaptic handshake.
And the things that carry that message across the gap, those are called neurotransmitters. They're the brain's chemical mailman. So when that electrical spark hits the end of the line, it's like a trigger that tells these tiny little bubbles filled with neurotransmitters to release their cargo. They spill out, float across that tiny gap, and deliver the message to the next neuron in line.
Now this is where things get really, really interesting. Because that chemical conversation, that handshake between neurons, that's where we can step in. If you can change that conversation, if you can mess with those chemical messengers, you can actually change how the brain works. And that, my friends, is the entire idea behind neuropharmacology.
When you boil it all down, pretty much every drug that affects our brain has one of two very simple goals. Goal number one, turn up the volume on a specific signal. Or goal number two, turn the volume down. It's really that simple. They either make more of a chemical messenger available, or they block it, making it harder for the signal to get through.
So how exactly do drugs do that? How do they turn the volume knob? Well, this here is the pharmacist toolkit. These are all the different places a drug can act to change the conversation. You can block channels, you can interfere with the little enzymes that build or destroy neurotransmitters, you can even mess with the pumps that are supposed to clean everything up. Now don't worry about memorizing all 8 of these. Let's just look at a couple of real-world examples to see how it actually works.
Okay, let's take a famous example. SSRIs, a super common type of antidepressant. They go after target number 6 on our list, the reuptake pump. Think of this pump as a little vacuum cleaner that sucks up leftover serotonin. Well, SSRIs basically stick a piece of gum in that vacuum. So the serotonin isn't cleaned up as fast, and it hangs around in the gap longer, sending its signal over and over. In other words, it turns the volume way up on serotonin.
Here's another one. Some drugs used for Alzheimer's disease, they go after target number 5. That's an enzyme whose whole job is to chew up and destroy a neurotransmitter called acetylcholine. So the drug blocks that enzyme. With the destroyer out of commission, more acetylcholine sticks around, which can help with things like memory and thinking. See? Different drug, different target, but the exact same principle. Turn up the signal.
And this table here, this really puts it all together beautifully. You can start to see the logic, right? For something like Parkinson's disease, where we know there's a problem with too little dopamine, the goal is pretty clear. enhance dopamine signaling. For schizophrenia, where some symptoms are linked to too much dopamine, the goal is the opposite, decrease it. Every single one of these treatment strategies comes directly from understanding that chemical conversation in the brain and figuring out how to tweak it. But, okay, there is one final massive hurdle. It's like the final boss in a video game. You can spend years designing the absolute perfect drug that hits the exact right target, but it's completely useless if you can't actually get it into the brain. And let me tell you, the brain has an insanely good security system.
It's called the blood-brain barrier, or the BBB for short. Just imagine the most exclusive nightclub in the world. The BBB is the bouncer. It's this super tightly packed layer of cells lining all the blood vessels in your brain, and its job is to keep pretty much everything out. Viruses, bacteria, toxins, you name it. It's there to protect the brain's incredibly delicate environment.
Now, there are a few secret handshakes to get past this bouncer, but the most common way for a drug to get in is that first one on the list, passive diffusion. This basically means the drug has to be designed like a ghost. It has to be really small, and this is key, fat-soluble. That lets it literally dissolve its way right through the cell walls of the barrier and sneak on in.
And that, right there, is the huge central challenge for anyone designing brain drugs. It's a two-part mission. Part 1, your drug has to be like a master key, shaped perfectly to fit one specific lock inside the brain. But Part 2, it also has to be a master of disguise, sneaky enough to get past that bouncer, the blood-brain barrier, in the first place.
So, that brings us full circle, doesn't it? But hopefully with a whole new way of looking at it. We are living in an age where we have the tools to literally go in and edit the chemical conversations that create our thoughts, our moods, our very consciousness. The power of that is, well, it's immense, and it leaves us with one final, very big question.